So hello, welcome to my sixth video. Will be on wet clean and wet etch. So let me get started. Alright, on wet clean first. So the problem when we do our fabrication of semiconductor wafers is that many of the processes involves steps that can create a contamination. So contamination can be in terms of particles, right? It can be in terms of like elemental contamination, elements that's not supposed to be in there, right? Gets into your wafers. So these are all big problems for microfabrication. So for example, if you have a particle on a photoresist, it will block certain areas that should be exposed to your UV light during exposure, right? But the area is now blocked by the particle. So certainly it will affect the photolithography patterns that is patterned onto the wafer during the development step, right? In addition, right, if let's say a particle falls on the wafer surface, falls on the feature itself, right? If it falls on the feature, what happens is that it creates a inclusion or a certain area that where your subsequent deposition or subsequent steps that you need certain overlay on top would definitely be affected by the presence of this particle on your features. And in addition, right, if we have like metallic contamination, we have metal ions, heavy metal ions that diffuse into the semiconductor material. It will also affect the electronic properties of the material, which will subsequently affect the electronic characteristics of a device and therefore its usability as a proper device. So that's why, right, we need this idea of cleaning and stripping whatever contamination that we have on our wafers. So let me first introduce this idea on the wet and also the dry photoresist strip. So the thing is that when you are done with your photoresist, when the photoresist has really served its purpose, we need to remove it. So when we remove it, we need to make sure we remove it well, because if not, there would be residue of photoresist, especially in these like areas there's a troughs, right, the vias and all that kind of thing. So that would be problematic because your photoresist will remain there and it will be a contamination for any subsequent fabrication steps. So that's why, right, we need methods to strip the photoresist. So there are two ways to strip your photoresist. The first way is to use an acid and a strong oxidant, and this basically oxidizes your organic photoresist because your photoresist is an organic compound. So this combination of oxidizing acidic environment is able to oxidize your photoresist into carbon dioxide and water, right? And if we can do this oxidation in a wet environment, it turns out we can also do it in a dry environment, right? In a dry environment means it's not in like a solution, it's not in an aqueous solution, right? Instead, the second way, which is like a dry photoresist strip, is the use of oxygen plasma to convert the resist. So we know that, you know, for example, your organic compounds can be combusted in air, right, to form carbon dioxide and water. So this is something similar, just that in this case is the use of oxygen plasma, because plasma species in a plasma are high in energy, so they have more than enough energy to trigger the oxidation reaction to convert your organic compound, that is your photoresist, into carbon dioxide and water. Okay, and so this step is also sometimes called etching, right? Plasma etching or oxygen etching. Okay, so it turns out that we can use either of these, but sometimes we have certain cases where we prefer one over the other. Right? For example, photoresist removal in back-end processes, you may want to use more of the oxygen plasma, especially if your metal interconnects are exposed. This is because in the back-end process, you already have a lot of the metal interconnects, your copper interconnects, for example. Nowadays, you mostly use copper. So the thing about copper is that it oxidizes pretty easily. So if we have the use of a oxidizing agent in an aqueous solvent that's also acidic in nature, right, what happens is the oxidation of copper will occur pretty quickly, and that's bad because when you have a layer of, let's say, oxide of a non-conducting, electrically non-conducting oxide, right, in between, let's say, two layers of metal, so these two layers of metal is supposed to contact each other and supposed to be able to transmit, to conduct electricity, your electrical signal. But now you have a layer of insulator between them. That's the problem, right? Certainly it will increase the resistance of the circuit. If not, it may even actually cause a break in the circuit completely, right? So that's certainly not desirable because it will affect the electrical performance of your eventual device. So that's why in the back end process, we normally tend to use, if possible, like this kind of dry etching, right, or dry photoresist strip through the use of oxygen plasma. And if your metal is exposed, we tend to avoid the wet steps, right? Also because, right, in a wet solvent, we may have other kinds of corrosion that may occur to the metal, right, like a galvanic corrosion, etc., etc. So that's also something that we want to avoid. So now I'll cover two very common cleaning agents that's often used to remove particles from the wafer surface. So the first is SC1. So SC1 is basically a high pH cleaning agent. So it's the use of ammonia, right, H2O2, hydrogen peroxide, and water in basically in a certain ratio, right? And it's normally conducted at an elevated temperature, right? Not that high, right? Because we are of course limited by the boiling point of water, but basically 7 to 80 degrees. It can be for a certain time, like 10 minutes, and yeah, basically the pH is high because of the presence of ammonia. So sometimes they write it as NH4OH, right, to represent that ammonia is aqueous, right? In the aqueous state, it's ionized, it's dissociated in the aqueous state. Okay. So the purpose is that this is able to oxidize organic contamination, right? Why? Because of hydrogen peroxide, right? And in addition to that, the presence of ammonia is able to form soluble ammonia complexes, right? Such as this one, CuNH342+, right? With certain metals, right? Especially, right? Like some of these metals like copper, like your transition metals, right? They actually form soluble ammonia complexes, right? And so the good thing is that this cleaning agent is also able to slowly dissolve the native oxide layer on silicon, right? And and eventually a new oxide layer will grow back. And so that's good because it removes the particles on the oxide. So you can think of it, the particles are resting on your silicon surface. There's a thin layer of native oxide. So when this cleaning agent removes the layer of native oxide, it removes the particles together with it. And that is because, right, ammonia is able to lightly etch away silicon. But the problem is that this will make the surface a bit rough, and so this less ammonia, right, is used to this. So sometimes you will tune the ratio of ammonia to be lesser. Okay, and so if you have SC1, right, turns out we also have the SC2. So SC2, in contrast, is a low pH cleaning agent. So SC1 is alkaline, SC2 is acidic, and so we still have a hydrogen peroxide dissolved in water, but now we use a hydrochloric acid instead of ammonia. And so, yeah, what it does is that it removes alkali ions and certain cations that form insoluble hydroxide in basic solutions like SC1. So remember in SC1, right, your ammonia is able to form soluble complexes with certain species of metal ions, right, like copper, like your zinc, like your silver and gold. However, certain metals, right, for example, Mg, right, Fe3+, right, Al3+, what happens in like ammonia solution is that they actually form an insoluble metal hydroxide. And so that's not good, right? Because then it precipitates out your metal hydroxide that can then rest on the surface, and then it becomes a particulate contamination. So that's not desirable. So what we do is that we use SC2 to dissolve these insoluble hydroxides through an acid-base reaction, right? Because your SC2 is an acidic solution, and then it's able to wash away the dissolved ions. Okay. And in addition, right, SC2 also can further complete the removal of any metallic contaminants such as gold, right, through an oxidation reaction, right? They may not have been completely removed by the previous SC1 step. Okay, so now I'll discuss briefly the significance of H2O2. So I want you to take a look at this table over here. So note that this is standard oxidation potential. Some of you may be more familiar with reading things in standard reduction potential, right? This is the same, just that it's defined with the forward reaction being the oxidation reaction. Okay, so it's like the negative of a reduction potential. Okay, so what happens is that we see that if we, let's say, only have, right, Si and Fe, right, the oxidation potential of Si is more positive than the oxidation potential of Fe. So what happens is that Si will be preferentially oxidized to SiO2, and Fe3+ will be preferentially reduced to form Fe. And so what happens is that Fe, which is iron, right, gets plated up, it gets precipitated on your silicon surface. Right? However, if you have H2O2, right, if you have H2O2, we see that H2O2 is preferentially, right, is preferentially reduced over Fe3+, right? It's preferentially reduced over Fe3+, right, because it has a more negative oxidation potential than your Fe3+, Fe couple. Right, so what we see here is that your H2O2 will be reduced and your Fe will be oxidized to Fe3+. And when your Fe is in the oxidized ionic form, it can dissolve in the solvent and be washed away. Okay. So one thing that we sometimes do in wet clean is to have this ultrasonic agitation. So if you have been to a spectacle shop, you may see them before, right? Before they give you your new pair of spectacles, they'll put your spectacles in an ultrasonic clean bath, right? You put it in a like small metal tank filled with water that zzz, right, it vibrates. And what actually is happening in the ultrasonic bath is that ultrasonic sound waves are being passed through the water, and this creates bubbles in the water that are formed then collapse, and so this creates like a rubbing action, right, an abrasive action on your surface of your material. So if your spectacle glass, right, it removes all your dust, all your dirt, all your oil that's on your spectacle lens, right, through this action of the they call cavitation, forming and cavitation of the bubbles in the water. So same thing here, right? We can use ultrasonic agitation by using high frequency vibration, like sound wave vibrations is the same thing, right? Between, normally they use 20k to 45k hertz, right, kilohertz, right, to cause this cavitation of the bubbles that is able to scrub, to agitate, to remove any particles that's on the surface. Okay. So let me give you an overview as to what is called the standard RCA cleaning procedure. So for example, we can start off with your Piranha solution, your H2SO4 and H2O2 that is able to strip your organics, especially your photoresist, right? That's a very important organic substance that's often on your wafers that you need to remove. Then after that, you may want to use like hydrogen fluoride to strip the chemical oxide. However, the main problem with this is that it introduces a hydrogen passivated surface. That means it will make your silicon surface is terminated with SiH bonds, and that's not good because SiH bonds, right, have a certain property where it is easier for certain particles to adhere on and be attracted to a surface passivated with SiH bonds, right, compared to your let's say maybe your standard silicon surface, maybe with a tin native oxide or something like that. And so this step nowadays, right, is sometimes skipped because of that reason, right. So after that, what they do is that you can do a DI water rinse, right. Then after that, we can do your SC1. Remember your basic solution first. Then a rinse, right. Of course, you have to rinse it first before changing to acidic solution, right. Acidic solution is your SC2. And then finally rinsing, and then you have to spin dry the wafer, right, for the next step, because oftentimes moisture is not good for many steps, right. So if you wash it with an aqueous solution in DI water, you need to find a way to dry it. So there are a few ways to dry it. I'll not cover it in this video, but one of the way is spin drying the wafer. So similar to how spinning can help to coat the photoresist evenly, if you spin even faster, any liquid on your wafer surface will be spun out as well, spun out of the wafer. Okay, so now I cover wet clean, so now I cover wet etch. So the difference, the wet clean is to remove and clean the surface. So clean contaminants, clean photoresist, it basically just is like taking a mop and just mopping all the dirt off your floor, right? But wet etch is different. Wet etch is to etch out, to carve out patterns, right? So where you want to remove materials is selective. It is well defined. You only want to remove materials where you want to remove it. And areas where you don't want to remove, you better not touch, right, in your wet etch step. So that is the difference between wet etch and wet clean. So there's certainly a lot of requirements that's now needed for wet etch, right? Certainly a lot more requirements. One of these requirements is directionality, also known as anisotropy. So directionality is how directed the etching is, right? You only want to go in one direction. You don't need to go left, right? You only want to go straight, for example, right? You want to go straight. You don't need to go to the left or to the right, as an analogy, right? So this diagram here shows it very clearly. If you have a completely directional etch, right, we have a sharp edge, you want to etch down only, so you etch it down. Okay. However, when you have an isotropic etch, it etches in all directions evenly, so you start to see a curvature, a curved surface, right? Why? Because it starts etching not just down but left, right, and right, correct? So it forms a curved surface, right? So another term for this is basically isotropic versus anisotropic, right? So iso means the same, right? Isotropy means the same in all directions. So when you have a resultant curved etch profile, right, we call this isotropic, right? Because it is, the etch occurs equally in all directions. Isotropic, same in all directions. However, when we have a directional etch, right, straight down, for example, we call this anisotropic, not the same in all directions, but in the specified and preferred direction only. So we can have a factor that quantifies this directionality or anisotropy, called the degree of anisotropy. So you just take your lateral etch rate, which is the etching in like the left and right directions, over your vertical etch rate, right? And you want minus that ratio. So if let's say you do not etch to the left or to the right at all, this numerator is 0 and your degree of anisotropy is 1. It's perfectly anisotropy. The anisotropy degree is unity, right? However, if your lateral etch rate is at the same rate as your vertical etch rate, that means it cannot distinguish between left, right, and down, right? It is the same in all directions. Then your this fraction over here will be 1, and 1 minus 1 will give you 0, right? So it's not anisotropic at all. It's perfectly isotropic. Okay. So you may think, right, the directional etching is good, right? Because you etch straight now where you want it to etch, right? You don't go left, right, wherever you want to go, right? However, right, sometimes you want a bit of a bit not completely anisotropic, right? Not completely anisotropic, right? Why? Because if we do the vertical etching, we have like sharp corners like this, right? Sharp corners like this. However, what's the problem with sharp corners like this? Is that when you do the next step, you may not be able to get a good coverage, right? So maybe you want a more curved profile sometimes. Sometimes you want a more slanted profile. It may be better for subsequent processing steps. That's something you have to consider. Yeah. And the second thing is etch selectivity, right? Because not only do you want to specify how your etch profile turn out like, which is your directionality issue, you also want to specify how well your etch selects for one material over the other, right? How well the etch selects for one material over the other. Okay, right? Because we have a mask on top of your wafer that defines the pattern where you are going to etch and where you are not going to etch, right? And so your selectivity for your material must be greater than your selectivity for the mask. If not, right, let's say you want to etch like a 5 nanometer deep trench and your mask is maybe only 3 nanometer thick. Okay, if you etch your silicon at the same rate as your mask, by the time you etch 3 nanometer in your silicon, not even reaching your desired dimension yet, your mask is gone. It's all eaten away already, right? That's not good, right? That's not good. So we want, right, of course, an etch that's able to have greater selectivity for the thing you want to etch and less selectivity for the thing you don't want to etch. Okay, so generally we can say that etching that occurs by a chemical mechanism has a higher selectivity, right? Why? Because chemical reactions are selective. A can react with B, but C maybe cannot react with B, for example, right? For example, SiO2 oxide, right? Oxide normally can react with acid, right? But can silicon react with acid? Maybe much slower, right? For example, right? For example. However, if you use a physical etching mechanism, that means like physical etching is when you use like energy to bombard material away, right? We'll learn more of this in the next video. But for example, if you, let's say, imagine use a cannon, right, to shoot a cannonball. I don't care whether your wall is made out of concrete or made out of bricks, right? If your cannonball is powerful enough, both walls will collapse, correct? Right? So physical etching has lower selectivity in that regard. Okay, so I'll cover a wet etch, right, in this video. So most wet etch processes are isotropic because it's a chemical reaction. You cannot tell the chemicals, hey, go there, hey, go there, or here or there, right? You cannot tell them that, right? If your surface is in contact with the solvent and the solvent is carrying your reagents, the chemical reaction will happen on all the surfaces, right? Your chemical reaction will happen on all the surfaces in contact with your reagents, right? So for example, if you want to etch SiO2 with HF, right, to form H2SiF6, okay, plus 2H2O. So these two compounds are H2SiF6 is soluble in water, right? So you dissolve away. You cannot say that the silicon dioxide here downwards must react, but silicon dioxide to the left and to the right cannot react. No, as long as it's in contact with your solvent in your reagents, as long as it's not masked, it's in contact with your reagents, it will dissolve away. Okay. So what happens in this etch is that normally, of course, a chemical reaction occurs, and when a chemical reaction occurs, your reagents have been consumed, right? So HF is being consumed, and so the etching rate actually decreases over time because your concentration of HF decreases over time. So what they normally do is to use HF with a buffering agent, right, such as NH4F. So if you remember the idea of a pH buffer, it maintains a constant concentration of your hydrogen ions, right, because of this idea of the equilibrium of the solubility, or rather the dissociation equilibrium, right? As one side is being consumed, the equilibrium position will shift to offset the change. So as HF is being consumed, the NH4F to produce NH3 and HF, this equilibrium, right, will shift to the right to produce more HF to compensate for the consumption of HF in the etch reaction. Okay, so this is called a buffered HF or buffered oxide etch, BOE. It's quite a common term. Okay, so let's take a look at etch rates to find out the selectivity, right, selectivity of this kind of oxide etch. So it turns out that this kind of buffered oxide etch etches your thermal SiO2 and your quartz. So these two are both silicon dioxide at a very fast rate, but your silicon close to not etching it. Your nitride, right, close to not etching it. Correct. So the thing is that we can see that this buffer oxide etch has an extremely good selectivity for SiO2 over silicon. Okay, and if you see something like Pyrex, right, it also contains a bit of like SiO2 kind of species, right? There's somewhat of an etching of it. Okay. Right, and if you see phosphoric acid is different. It's a very selective etch for nitride. It etches nitride at this 4.5 rate, right? As for silicon and oxide, at a much lower rate. So phosphoric acid is a good selective nitride etch. Okay. Yeah. Right. However, the problem with isotropic etching, right, is that it causes this undercut, right? Because I told you it is this curvature of the surface, right? Curvature of the surface. With the etch, right? Because it's etching in all directions equally. So what I have is this undercut, which it may be a good thing for certain purposes, but in many cases it's also not a good thing. Yeah. So we mentioned so far that wet etch is normally isotropic. However, is there a case? Is there a situation where wet etch can be anisotropic? Yes, actually there is a case, right? The anisotropic wet etch of silicon. Okay, so silicon. So why is this so? This is because, right, certain crystal faces of single crystalline silicon is easier to etch, right, by these etching reagents, KOH or TMAH, right? TMAH is trimethyl ammonium hydroxide, right? These etching agents, right, etch certain faces of silicon at a faster rate than others. Right? And what's the reason for that? Actually very simple, right? You look at this 100, look at 110, look at 111. And then which rate, right, will have the fastest etching rate, right? And which one will have the slowest etching rate, right? The answer is that the slowest etching rate is your 111. Why? Because you can see that in a 111 plane, I have so many silicon atoms. That means to remove one layer of the plane, I have to break much more silicon-silicon chemical bonds, right? Per surface area, I have more silicon atoms. So per plane I remove, right, in that direction, I have to break more silicon-silicon covalent bonds, right? And that will take longer, right? Because it's a chemical reaction after all, right? It's a chemical reaction, right? It will take longer to happen. And so what happens is that we tend to get these profiles, right, where your 111 phase that etches so slowly, right, is still not completely etched, right? So there is this slanted profile, and so we can see that it's somewhat like a pyramidal shape. Right, so this base here, 110 is like this base here, and this 111 are like these slanted edges over here. So it's like a bevel, sunken bevel kind of profile. Right. So let's take a look at some wet etching chemistries. Right, for SiO2, right, it's an oxide, so it makes sense to use an acid, and it turns out HF is very good. However, HF is a big health hazard, because if HF contacts your body, right, it's not just corrosive as an acid, but the fluoride ions, right, will react with like your calcium ions in your body, and it cause like a kind of decalcification, right, of your body chemistry. So you have to use an antidote if you ever encounter or come into contact with HF directly on your skin or on your eyes, things like that. Yeah. So for nitride, we can use HF. However, to be selective, we can use phosphoric acid. Okay. For aluminium, we can use this combination of reagents. For polysilicon, we can use this combination of reagents. So if we use, right, this combination of reagent, right, nitric acid, right, in water and HF, right, this etch is not considered crystallographically selective. It's not considered anisotropic, where it selects for certain planes faster than others. Why? Because this combination of reagent doesn't directly etch silicon. The nitric acid actually oxidizes silicon, and that silicon dioxide, which is an amorphous material, it's not, there's no like a clear crystal planes, right, is then dissolved by HF. So this is much less dependent on your planes, on your crystallographic orientation of your silicon. Okay. For TI, we can use SC1, TIN, also a very common conductive contact used in semiconductor devices, is also SC1. Right, your titanium silicide, also a very common contact materials, right? You can use this buffer oxide kind of buffer oxide etch kind of combination. For photoresist, the Piranha solution that we mentioned earlier already. Okay, so I just show you like how a wet bench may look like in a semiconductor fab. So we have the different trials. So for example, this is your etch, right, solution. Then after that, you clean in your DI water. Or this can be your SC1, your SC2, and then your DI water, for example, or a Piranha solution, some other cleaning solution, and DI water. And there can be many more trials, of course, not just 3. In fact, there are often many more of them, because your wafer needs to go through successive solvents, especially like after going through one solution, right, you may have to clean in DI water before moving to the next solution, and so on and so forth. So it's many trials. Yeah. Okay. So I end this video on the wet etch and wet clean. So in the next video, right, I'll talk about dry etch. Okay, dry etch. So dry etch in the plasma etch. So that is actually a very complex topic with many actually concepts that needs to be mastered. So that will be a much longer video.